Hi everyone, I'm Professor Beiersdorf. I'll be your instructor this quarter for Chem 216. You may have already gone to our introductory Zoom session. If not, in it I will explain everything on how this class will work. Okay? But overall, each of these lessons will start with something that looks like this. It'll show you information on when the lesson is due, and when you have to do your homework associated with it. For instance, this one has homework via Sapling that is due on Monday, 4/13. In addition, it has a schedule of what's going to be happening during our scheduled class time. For instance, this week, it'll start off with an introduction and then office hours for the other two sessions. Notice lesson 2 and 3 will be coming. Labs will start on Wednesday or Thursday. Watch your email for more information. Okay, also on these first pages will be a review. This is, for instance, a review of Chem 215. So what is the law of conservation of mass? And delta H for a reaction is negative 45 joules. Is it endothermic or exothermic? These are two topics that we'll be covering in this first lesson. All right, so the law of conservation of mass states that mass or matter isn't created or destroyed. This is why we had to balance chemical reactions. The second one, when we talk about delta H of negative 45 joules, that means that the reaction is giving off heat, and therefore it is exothermic. We'll talk a lot more about that today, and in fact, the relation of heat to a reaction is thermochemistry. That's what we're going to be talking about in this first lesson. Thermochemistry is the study of the heat released or absorbed during reactions or physical changes. This is in chapter 5, the first two sections. And so when we talk about reactions in Chem 215, we talked about something like this. CH4 plus 2O2 going to CO2 and 2H2O. This is what happens when we turn on a stove, right? Natural gas, which is methane, burns. And we dealt with the law of conservation of mass. That's why we had to balance this. But why do we burn things? Well, we burn it not to create CO2 and water. The reason why we burn things most of the time is because we want to get out of it heat. Right? That's why we burn logs on the stove, etc. And we can talk about reactions based on their heat as either being exothermic or endothermic. Exothermic is a reaction that releases heat. Heat is a product. Eventually, I'll get better at this writing. In fact, eventually I'll get my iPad set up, but heat is a product when it's exothermic. When it's endothermic, that means it's reabsorbing heat, and therefore heat is a reactant. We know all about exothermic reactions. Fire, exothermic reaction. But an endothermic reaction, well, those are kind of the opposite of exothermic. For instance, let's say we have an ice cube and we want to turn it into water. What do? We put heat into it and it turns into water. So thermal chemistry is just talking about heat. And we'll talk more about heat in a little bit, but it's part of a broader topic called thermodynamics. And thermodynamics is not just talking about heat, but other types of energy. We'll expand past thermochemistry in a little bit. All right, but before we do that, let's talk about energy. Energy, when we talk about it in physics, we can talk about two types of energy. We talk about kinetic energy and potential energy. And this biker on the top of a hill, if he's not moving, he has only potential energy. Energy due to his position. But as he moves down the hill, now he has kinetic energy. He's moving. That's energy due to motion. And As he goes down the hill, he gets less and less kinetic energy until at the bottom of the hill, if we were down here, now he would have kinetic energy, but he'd have no potential energy. The same holds true for things like a dam. This is the Hoover Dam, right? All this water up here has potential energy, and that water goes down the side, and they actually use that to generate electricity. All right, but in chemistry, we're not really talking about kinetic and potential energy. We're more talking about reactions, and we're talking about composition. So inside each compound, we have bonds, and these bonds are an example of potential energy. And we did problems like this in Chem 215, where we looked at bond energies in order to figure out delta H being the heat associated with it. We'll talk about that a lot more in 216. Okay, so let's first talk about some energy changes. So when we talk about energy changes, just like we have the law of conservation of matter, we also have the law of conservation of energy. And law of conservation of energy says that when we have a reaction, energy is neither created or destroyed, but we change forms. For instance, this biker at the top of the hill, he has high potential energy but no kinetic energy. And as he goes down the hill, that potential energy is getting turned into kinetic energy. Right? But the total energy is constant. Now, what is energy? We've used energy already in this class, and we use energy in everyday life, but what does it mean, energy? Well, energy is the capacity to supply heat or do work. This is what we think about when we want to use energy in everyday life. If I have some soup and I want to heat it up, I put energy into it. That's heat. Or if I want to go for a run, I might say, no, I don't have enough energy to do it. Don't have enough energy to do work. All right, so these two factors, heat and work. Heat we symbolize with a Q, and work, which is movement of matter, we symbolize with a W, a lowercase w. And we can sum these up, and we have something called internal energy. Internal energy is all the energy inside a compound. These can be translational, vibrational, or rotational molecules. So I have here a bunch of molecules. They can be vibrating a little bit, or they could be moving. And as temperature decreases, U decreases. Or as temperature increases, U increases. So as the temperature increases, these move even more. Okay? We abbreviate this as U, but sometimes we could also abbreviate it as E for energy. And because we have conservation of energy, what we can say is something called the first law of thermodynamics. The first law of thermodynamics states that the internal energy of a system changes due to heat flow into or out of the system and work done on or by the system. In other words, we have conservation of energy. This can be symbolized by this equation here. Delta U equals Q plus W, where Q is heat and work is W. So how do we get an increase in U? Right? By the way, remember delta? Delta means change. We'll talk more about this a little later. All right, so how do we increase U? One way to do this is to add heat. That would mean Q is positive. The other thing we can do is do work on the system. That would mean work is positive. Now, work doing on a system or performed to the system doesn't quite make sense, but let's think about the opposite. To get a decrease in U, we could either have a loss of heat, meaning Q is less than 0 or negative, or work can be done by the system. If I'm the system and I go for a jog, I'm doing work, so I lose energy. So my work would be negative. Okay, so we have these two ways. We can either have Q increasing and W positive, and that can make a delta U that's positive, or the opposite. One thing we should talk about is expansion work. Expansion work is, let's say I have some air here, and it expands. What's happening? This air is expanding, so it's doing work. So that means W is negative. If instead I were to contract this down, so take this air and squeeze it together, that would be a case where it is actually a positive W. So let's look at a problem. Let's say we have a system that does 25 kilojoules of work and gains 295 kilojoules of heat. What is the change in the internal energy of this system? All right, so let's go to the whiteboard here. All right, so first, we're going to talk about internal energy. So we need to talk about delta U. And we said that delta U equals Q plus W. So the key thing is we need to figure out whether my Q is positive or negative. Let's see what it says. It says for my W, it says it does work. If I do work, that means my W is going to be negative. That's negative 25 kilojoules. By the way, we don't talk about this, we'll talk more about this later, but remember, in the same way that 1 kilometer is 1,000 meters, 1 kilojoule equals 1,000 joules, where joules is the unit of energy. Okay, so that's my W. What about my Q? I say that it gains heat. So that means that my Q is going to be positive. In this case, it's going to be positive 295 kilojoules. So I have my delta U equals 295 kilojoules plus minus 25 kilojoules. So that's going to work out, and I'm going to get 270 kilojoules for my delta U. All right, so let's go back and let's look at some more examples. So when I first talked about delta U, I talked about W being work, movement or matter, but I really didn't say what heat is. I kind of just said, we know what heat is. So let's talk about this in more detail. All right, so heat, in order to understand it, we need to think about thermal energy. So if I have some water right down here and it's boiling, what that means is that those water molecules are moving around, and eventually they'll move around enough that some actually go in the gas phase. When it is colder, they're moving around less. This is kinetic energy due to molecular movement. We quantify this as temperature. And usually as temperature increases, substances expand. Well, so thermal energy, so if I have something that's high temperature and low temperature, and I put them into contact, what's going to happen? Well, if I put something, I have my hand here, I'm like, ooh, it's too hot, I might put an ice cube on there. What's going to happen? My hand's going to cool down, and that ice cube, it's going to actually heat up. So energy is going to go from that high temperature side to the low temperature side. And so this will get a little bit cooler. The low temperature side will get a little hotter. This transfer of thermal energy, this is what heat is. Heat is by definition flow of thermal energy. So sometimes we say things like heat flow. Well, heat flow doesn't make sense. Heat flow is just heat, right? You can only have heat if you have a flow of energy. Now, what's going to keep on happening? Well, eventually, this hot side is going to keep on giving off energy until eventually they're the same temperature. This is called thermal equilibrium. Thermal equilibrium is when I have the same temperature on both sides. At this case, they're not going to change energy, right? They're going to stay that temperature. Okay, so we have energy is capacity to supply heat or do work. And we said heat is thermal energy transfer and work is movement of matter. How do we measure it? Well, in food science, we use calories, where a calorie, CAL, is the amount of energy to raise 1 gram of water by 1 Kelvin, or 1 degrees C. Now, actually in food science, we use something called a calorie with a big C, where 1 calorie with a big C is 1,000 calories with a small c. And this is actually what we see on a food label, right? It'll say 22 calories, and that is 22,000 of these lowercase calories. But we're not going to use calories in this class. Instead, we're going to use that joules we talked about. 1 joule is actually 1 kilogram times meters squared over seconds squared, right? Because joules is derived from each of these other factors, kilograms, meters, and seconds. But for this, what we should know is that 1 kilojoule equals 1,000 joules. All right, so let's move on, and now let's talk about something called heat capacity. Heat capacity is the amount of heat a body of matter needs to absorb to change its temperature by 1 Kelvin, or 1 degree C. Now, I say here change the temperature. We can symbolize this by delta T. And whenever we have a delta, that represents a change in something. And so we're looking at the final minus initial. So delta T is the temperature change. So T final minus T initial, or TF minus TI. Okay, now the heat capacity of something is dependent on 2 things. The type of the matter, for instance, this pan versus this pan. Notice that this pan has a metal handle, whereas this one has a plastic one. If I had this pan over here on the left on the stove, well, I wouldn't go, or on the stove top, I wouldn't go and grab it because that handle is going to be hot. That's because this is going to heat up. This plastic has a different heat capacity. The other thing that heat capacity is dependent on is the amount of matter. We know this because if we had a small pot versus a big pot, this big pot is going to take more water or more heat to increase temperature. And now, because this is dependent on the amount of matter, we can say that heat capacity is an extensive property. Extensive means it's dependent on the amount of substance. All right, so let's go ahead and let's do a problem involving heat capacity. All right, so by the way, heat capacity is represented by a big C, and it's equal to the amount of heat, Q, over delta T. And so heat capacity can either be in joules per degree C or joules per Kelvin. Either one will give you the same answer. All right, so let's say we have, let's say we're told it takes 18,150 joules to increase the temperature of a frying pan from 25 degrees C to 65 degrees C. And we're asked what its heat capacity is. All right, so we're going to use C equals Q over delta T. We're told what Q is, because we're told what the heat is. So it's 1,800, 150 joules. And now we need to find delta T. Well, in order to do delta T, we need to do final minus initial. Well, we're going from 25 degrees C to 65 degrees C. So that means our final temperature is 65 degrees C, and our initial is 25 degrees C. 0.0. All right, so that's going to give us 65 minus 25. That's going to give us 40.0 degrees C. Delta T will not always be positive. Sometimes it will be negative. We'll see that in the next class. But in this case, it's positive. I put this into my calculator, and I try to figure out what I get. And when I run it on my calculator, I get 453.75. Notice we have joules over degrees C. All right, so this is what my calculator says. Well, notice this has 4 sig figs. This has 3 sig figs. So how many sig figs should my answer have? This is where in class I would say, hey, how many? And eventually you guys would say, so it's going to be a little bit different. You know, it's not like Blue's Clues where you have to say it out loud. But at these cases, if you don't understand it, hey, pause it and look it up. All right, so if this has 4 sig figs, this has 3, my answer should have 3 sig figs. This is going to be 454 joules degrees. So that is my heat capacity. Now, notice that this is going to vary. If instead I had a small frying pan versus a big one, the amount of heat to increase it is going to change. And so we really don't want to deal with heat capacity because it's extensive. We want to determine something that is intensive, meaning it's not dependent on the amount. Okay? This is kind of like you go to a store and you see something, you know, this yogurt is $1.62. This yogurt is 72 cents. So which is the better deal? Well, you might think, oh yeah, this one's a better deal because it's cheaper. But this one is a lot bigger. It's 32 ounces, whereas this one's 6 ounces. So sometimes on the store, they have something like this. They say the amount of money per ounce. So what did they do? They just took 162 divided by 32 ounce. They got 5 cents per ounce. Whereas this bottom one's 12 cents per ounce. So now which one's a better deal? This top one. Because it's cheaper per unit of yogurt. And so we can take an extensive property like price, or in our case, we're going to use heat capacity, divide by the amount, and that's going to give us an intensive property. And the amount we can either use mass or moles in order to do. Let's see an example. So when we do this, we no longer talk about heat capacity. We actually talk about the specific heat capacity. The specific heat capacity is labeled as a lowercase c. I know it's confusing. I know it's annoying, but it's the way it is. So lowercase c, the specific heat capacity, is the amount of heat to change the temperature of 1 gram of a substance by 1 Kelvin. Notice this is different than when we were talking about heat capacity. When we were talking about heat capacity, it didn't talk about anything about the mass. Okay? So, specific heat capacity is intensive. So it's awesome. It's also sometimes called just specific heat. And it has a similar equation, but now it's lowercase c is equal to Q over M times delta T, where M is mass. And it's now going to be in joules per gram degrees C. And specific heat capacity is better than just heat capacity. The reason being is iron always has the same specific heat capacity, whether this is a small amount of iron or a large amount. Okay? So you can see some different things. Iron has a different one than liquid water, different than ice. So let's look at an example. Let's say we have 348 grams of an unknown metal, and it absorbs 6.64 kilojoules of heat, causing a temperature increase from 22.4 degrees C to 43.6 degrees C. What is the specific heat capacity? All right, so we're going to use that new equation for specific heat capacity. All right, and so what's my Q? Well, I'm told 6.64 kilojoules. We know that for every 1 kilojoule, we have 1,000 joules. So that's going to get out 6,640 joules. What's my mass? My mass is 348 grams. And then my delta T, well, it says it's from 22.4 to 43.6 degrees C. That's 43.6 degrees C minus 22.4 degrees C. That's going to be 21.2 degrees C. Right? Now I can just plug those in. So my C, let's go ahead and just is going to be 6,640 joules over my mass, which is 348 grams, and then 21.2 degrees C. And so notice how this grams is important, because this grams takes into the mass of it. Okay? So I do this and I get 0.900 joules per gram degrees C. This is the amount of heat required to take 1 gram of the substance and heat it up by 1 degree C. Now this is nice because once I know what this C value is, I can have a whole bunch of these specific heats for different compounds, and I can see, all right, what is this compound? Well, it looks like it's probably aluminum, because aluminum has a specific heat of 0.897 joules per gram. One other thing with these specific heats or specific heat capacities, notice that they're all positive. Why are they all positive? Because a negative heat capacity wouldn't make sense. A negative heat capacity means in order to increase the temperature of something, I actually take heat away from it. That doesn't make sense. In order to increase temperature, I always put heat into it. So that means that my Q is positive and my delta T is positive. So that means I'll get something that's positive. Heat capacity is always positive. Okay, so let's go on and let's do another problem. But now here's a problem you're going to do by yourself. And actually, I will have this problem, the solution, on another video. So what you can do is you can do this problem and try to figure it out and then look at the answer. The key is not to just look at the video. If you just look at the video, you're cheating, and that's not cool. Well, you're not cheating in the class, but you're cheating yourself, right? Do it, try to figure it out, and then come for help. All right, so this one, we have 622 grams of aluminum. That's our mass. We're given C, and we're given a Q, and now we want to know the final temperature. So we're told the initial temperature. So what we need to do is we need to figure out delta T. So hint, you're going to start by rearranging this equation to get delta T, and then you can use that to get final temperature. Okay, so that's specific heat capacity. There's one other type of heat capacity we want to talk about, and that's something called molar heat capacity. Molar heat capacity is similar to specific heat capacity, but it's the amount of heat to change the temperature of 1 mole of a substance. Not 1 gram of a substance, but 1 mole of a substance. By the same amount temperature, 1 Kelvin or 1 degree C. Now, you can actually find the molar heat capacity, which is C mole, by taking the specific heat capacity and multiplying by molar. Why is this possible? Well, let's look at it for aluminum. Okay, so aluminum, we calculated its specific heat capacity is 0.900 joules per gram degrees C, and we want to know its molar heat capacity. Well, what I can do is I can take this, multiply it by its molar mass, and that's going to get me my molar heat capacity. Take this, 0.900 joules per gram degrees C, multiplied by the molar mass of aluminum. Where do I find that? I find that on the periodic table. Here's aluminum. Remember that number underneath there? That's my molar mass. That's 26.982 grams per mole. So notice what happens. I have grams on the bottom here, grams on the top here. They cancel out. So I'm going to get something that's 24.3 joules per mole degrees C. I end with 3 sig figs because I started with 3 sig figs. Okay? So notice, using those units, we did it in 215, we're going to do it in 216, you're going to do it in OChem, you're going to do it in biology. Always look at those units. So why do we have molar heat capacity and specific heat capacity? Well, they're just two different ways to look at it. But they're both useful in different situations. Okay, so that is it for this lesson. We talked about thermochemistry, which is the study of heat involved in reactions. We talked about energy, the first law of thermodynamics. Then we talked about specific heat capacity and molar heat capacity, okay? And just heat capacity itself. Remember, heat capacity is an extensive property, right? So we usually don't like this. Usually we want to talk about the specific heat capacity. Okay? There are problems in the book, but just like I said, we start every lesson with a page like this. We end it with something like this. So here's information on all the Zooms coming up, right? After this lesson, you should go and you should look at that worksheet. This is in the same location. You can see here, it has information on some key topics. It has that video problem that we went through. So go ahead and try that out. Look at this solution. And then it has some extra problems. These extra problems you can look at for the test and for study. Remember that homework number 1 is on sapling, and that's due Monday, 4/13. In 2 days, we'll post Wednesday or lesson 2, then lesson 3. And finally, labs start on Wednesday or Thursday of this week. All right, see you next time. Stay safe.